Okay, let's go. All right. What we're doing is the problem of
yeah, it's probably a really good one.
I only use it occasionally. No, but she was one.
okay.
I only use her. Not using the sense of like.
All right, we have a hemisphere.
Yeah. Wait, what is that?
Z square root of big R squared minus X squared minus Y squared. We have a density function. Was proportional to Z. Okay. And what we want to do is find the center of mass of this solid, this object of varying density. And what we did yesterday was we set it up 3 different ways: rectangular, cylindrical, and spherical. And because the spherical coordinates had those nice constants for limits of integration, we're going to do it that way. Okay? So let's do it. So the first thing is to find the mass of this object. And that would be the triple integral of our density function. Now our density function is kz, but we had to get that in terms of spherical coordinates. When we got that in terms of spherical coordinates, we found that z is equal to, and let me just go over that briefly here. When we go from rectangular to spherical, okay? We said that the cosine of phi is equal to z, this is the right angle here, over rho. So z is equal to rho cosine phi. Okay. That's how we get z in terms of our spherical coordinates. So we need k, z. Now, in addition to that, we need an integrating factor when we go to spherical coordinates, and that's a rho squared sine phi. And then we have a d rho, d phi, d theta. You can go in either order here. Okay? That will give us the mass of this hemisphere. The limits of integration, let's see, the rho limits we said were where to where?
0 to R.
Thank you. 0 to r. The phi limits? 0 to pi over 2. And we had a little question on that, whether that's going to be, should it be 0 to pi over 2, z-axis down to the xy plane, or should it be pi over 2 back to 0? We should find 0 to pi over 2 gives us the positive number that we want here. And that theta is going to go from 0 to pi over 2 as well, and we have to multiply by 4. Okay? So this should give us the mass. All righty? Yeah. All right, let's do it. Let's do it. All right, let's do it.
Well, we haven't done it yet.
No, we haven't. I just set it up. All right, let's integrate this with respect to rho. We got a rho cubed here. I'm going to take that k out front, okay? I'm going to end up with a rho to the 4th over 4 cosine phi sine phi d rho d phi d theta. Wow. And that I integrated with respect to rho, so I don't have this guy anymore. And I'm integrating from 0 to r. Okay? There's no d rho anymore. I did the integral with respect to rho. Okay? Now, What should we find to be the answer? The answer should come out to be in the very end, when we find the center of mass, the answer should be around 0, 0, r over 2. Around there somewhere. Maybe greater and maybe less, but it should be pretty close to being halfway up the radius, okay? Because we're making this thing more and more dense as we move towards the top, okay? All right, is everybody okay with this? Liam, you okay with that? I saw that. Okay. So, substitute in r, we get an r to the 4th over 4. We'll cancel this 4. So I'm going to get a k, r to the 4th. The 0 gives me 0. And then I have this double integral left. This is what we have left. Okay, now let's integrate with respect to phi. Wait, where's Dan? Ooh, we're doing this with no net, okay? Dan is our net with a Mathematica, right? No net, that's all right, we can do it. How do you integrate this with respect to phi?
Use substitution.
What is it?
Use substitution.
Use substitution, let u equal
Sine or cosine.
sine or cosine. Let u equal sine, the do would be cosine. You got a u squared, you got a u du, so it's u squared over 2. Okay, the cosine is our du part. Okay, so substitute in pi over 2. The sine of pi over 2 is 1. Sine squared is 1 then. Substitute in 0 to get 0. So we get a 1/2 out of that. And we're left with this. Okay. And the integral d theta is theta. And substitute in, we get pi over 2. So we're going to end up with our mass of this hemisphere, varying density, is going to be k r to the 4th pi over 4. Okay? That's the mass of that object. Okay. You agree, Brian? Then we know it's right. So, we don't even need Dan. Got Brian. Okay. All right, we ready? I'm going, and we're leaving this. Tim, you got it? David, you okay? Almost, okay. Okay. All right, that's our mass. Next thing we have to do is find the moment generated by this object about the xy plane. And that means we have to have a mass times a distance. And the distance from the xy plane is equal to z. So we need another z in there. So moment from the xy plane is equal to the 4 times the triple integral. Got the same limits of integration. Okay. Same limits of integration. We have a k we can take out front. But now we need another z, which is another rho cosine phi. So I'm going to end up with rho squared cosine squared phi, rho squared sine phi, d rho d phi d theta. Holy mackerel, look at that thing. It's awesome.
So does this mean we're going to have 3 different moments?
Have what?
Are we going to have 3 different moments?
No, I'm having a moment right now, actually. No. No, because the other moments are 0. What happens is, since the hemisphere is on both sides of the other axes, we don't even need to count to do those. The only thing that matters here is the moment generated above the xy plane. If we had the whole sphere, we wouldn't have to do anything, because the center of mass of that object would be 0, 0, 0, as long as our density function is kz, because you got positive and negative balancing off above and below the xy plane. But if you had a kz squared, then you'd have to do, again, the moment generated from the xy plane. That's what you'd have. But we only need one moment in this one because the other guys are 0. This is the only one we need. So, now that wouldn't be the case if we had a different density function. Now, if we had a density function of kxy squared z cubed, we would have to do those other ones because that center of mass would not necessarily be on the z-axis. Yes?
Did you just say it'd be 0, 0, 0 if it was kz?
Yes.
That's not what we're doing right now.
Yeah, but we have a hemisphere. If we had the whole sphere, kz as the density function would give us negative density below and positive density above, and they would all cancel out and give us 0, 0, 0.
So the kz function starts us off at 0?
Yes.
Okay.
Yeah, we have 0 density at the xy plane, and it's getting more and more dense as we move up off the xy plane.
That's why it'd be in the middle of like the top. It's like a
Yeah, well, that's why with a constant density, the center of mass of that hemisphere is not quite r over 2. It's less because you got more mass at the bottom of this hemisphere. But making the density function kz is going to move it up. It's going to draw it up. Does it draw it to halfway? I don't know. We're going to. That's what we're testing to see. Does the center mass become r over 2 or not? It may or may not. But without it, a constant density, it's definitely less. This is going to move it up, but how much up? We don't know. Okay. And if you were to do kz squared, it would move it up even more. And if you do kz to the n and let n go to infinity, what would we get for our center of mass of that limit? What would that limit be? What's that?
Could you repeat that?
Okay, I'll repeat it. Suppose we had a density function kz to the n, and then we let n go to infinity. What would we get for the center of mass?
Because it would go all the way to the top.
It goes to the top, and the top is 0, 0, r.
Oh,
Capital
R,
R.
okay.
Yeah, it would be 0, 0, r. That's what the limit would be as this thing got increasingly dense as we move to the top. Okay? It would approach 0, 0, r. Does that make sense?
Yeah.
Good. Let's do this one. This one here is equal to 4k. 0 to pi over 2. 0 to pi over 2. Now, we've got a row to the 4th. Now we're going to get a row to the 5th over 5. Cosine squared phi, sine phi. Rho is going from 0 to r. D phi, d theta. This is good stuff. This is good stuff. Substitute in. Oh, Carlene.
How are you?
Good. How are you? What's going
Well,
on?
my equipment isn't working and I have everything the way it should be. Could you just look at it for 1 second? I hate your...
Excuse me,
I'm
class.
so sorry to take your professor from you.
Don't break it, bro.
Should say. Oh, wait.
You're supposed to really mess up things on the recording.
Is that even
Oh, it's on recording.
backwards L?
Can we just like that's a D?
Man.
I don't know what is that.
That's a D, okay.
Oh, okay. Wait, what did you say?
Oh, that's
Backwards L.
Are you kidding me right now? It's not that. What are you?
I think that's pretty
Because
cool.
you know-
Intermission.
I didn't like grow up listening to it, but I did listen to it because even as I grew up.
I'm gonna watch it.
This piece of candy he's got.
Hello.
Yeah, dude, eat
The
it.
earth says hello.
We're just studying the video.
He's trying to get it on here.
You should do that.
Trying to get it on the can.
No, why? No.
I would love it just to see your face like.
Want to do it?
What's up?
Okay, so it's density is like more dense as it goes out. It's very.
Are we behind on that?
It is very.
Number 9 this week. Oh,
It's our last lap today, right?
I think so. We're behind on that. Yeah.
Because physics, they're done laps. They just have to present.
Think so, you're greater than reserve bracket?
We have magnetic balance and induction. Yeah.
Is it in class?
The induction one, yeah.
Where it's.
Where so does that mean we're not gonna have to do a second formal lab?
Why the double integral?
I'm all set.
You would be screwed if you had to do a second form before.
But it's only just.
Why? Just too much?
Yeah, it's like, I don't work with it right now.
Nah, I'm good. I'm not having enough fun yet. Let's turn it up.
Why not? But yeah, that's just how it is. Did it help? No. Two more.
I should have one. You got to finish it. Liam, you got to finish it.
All right. We did.
Oh, you did?
Yeah.
What did we get? What is it?
R/2, yeah.
It is R over 2?
No, we're just kidding. It's R over 3 times 45.
Oh, I should have known that. You know that?
Thanks, man.
Let's do it.
I can tell that just by looking at it.
Yeah. You guys are good. All right, substitute in R. We're going to get a 4K R to the 5th over 5. The double integral. And we got cosine squared phi sine phi d theta. Okay, now, what are we going to do this time?
Cosine.
Cosine. Dennis, you're great. All right, that u equal cosine. The du is a negative sign, though, so you got to be careful. You got to multiply by negative here and negative here. So we got negative 4k r to the 5th over 5. 0 to pi over 2. Our u now is cosine. The du is this negative sine phi d phi. So it ends up to be a cosine cubed phi over 3.
That's a negative sign?
Yeah, we need a negative over there because,
This will be negative 1/3.
yes, because what happens is you got to let u equal cosine, and the d is a negative sign, so you need to multiply by that up. My muscle memory is such that whenever I do this, it automatically makes a theta there. All right, but anyhow, that's a phi. So, what happens here is now we get this negative 4k r to the 5th over 5. When you substitute in pi over 2, the cosine of pi over 2 is 0. And then it's minus the cosine of 0, which is 1. So it's a negative 1/3. Okay. And now it gets back to positive, which is good. So we have 4k r over 5 over 15. The integral of d theta is theta. 0 to pi over 2. Wow, this problem is so cool looking. Wow. Okay. And that's equal to 4k r to the 5th over 15 times pi over 2, which is 2k r to the 5th over 15. That's the moment that this hemisphere generates about the xy plane. Therefore, it went nowhere. It went. Good question. It's the way. our center of mass of this object is equal to 0, 0. The moment from the xy plane to k pi r to the 5th over 15 divided by the mass, which is k r to the 4th pi over 4. Oh man, this is so cool, it's not funny. I can see it. I know, it's really neat. It comes out, okay, so, it's cool. 0, 0. Now what happens here? K's cancel, pi's cancel. We end up with this 4 coming upstairs with the 2, that's 8. R to the 4th cancel. We get 8R over 15. That is the center of mass. Just barely past midway up that radius. Just a hair past it, 1/15th. Oh no, half a 15th. 1/30th radius past midpoint. Wow. All right, what I'm going to do is I'll be right back. Let me get the test so I can tell you exactly.
That was great.
Number 1 is your 10 minutes.
3, C, 7, yeah, there's D on this one.
I mean, I guess this is it. We've already done his evaluation, so now he's just gonna like come into a problem and leave.
The next 2 tests are crazy impossible to do.
So now we have 8 E's.
Just doesn't try to teach us anymore, gives up.
Yeah.
The evaluation don't care.
Just go ask Toby, he'll teach you.
Just like leaves. Like,
just
goes
calls
here.
Toby.
Oh, he's
Toby's
here.
gonna save you at this point.
Teach us. Toby just came in. Oh, we were gonna do Calc 3 today, but we're so behind in physics.
Because we need to spend more time doing physics than Calc 3. Direct quote.
Whose ever name you write in this note?
Well, you got crispy then.
You're not showing the class.
So, someone in the front row really needs to put their head underneath that monitor so I can see their face whenever we watch this video.
I want to see every board.
That would be my reason to watch it.
Why don't you do that, Dylan?
Yeah, why do you have to be in the front row?
Because my face is
Keep
not
playing it.
attractive.
Front row.
That's Tim's over there.
What are you saying? They stand there.
Tim, I'm sorry, but you gotta go up.
Keep trying
Do it, Tim. Come on, Tim. Come on.
Tim,
Take over the
Tim.
team.
I'll do it. Someone's gonna do it.
Oh, yeah.
What we got?
Oh yeah.
Oh, put it there.
Wow.
We need something more intense though.
All right, bust it over your drawings out. Let's go, guys.
What's your
Yeah, man. Yeah.
you guys look at it for this week. Whoa. Brandon, why are you such a vulgar when we're in this class? I think this is an intervention for him. Guys,
It's getting real awkward.
please circle around right.
Brandon?
What's that? Don't post this video? Oh, what'd you guys say? Oh,
He said.
what else could you have done? All right, here we go. Oh, yeah, that's right, that's right. Okay, so this is test number 5. First part, 1 through 5, is I'm going to be giving you a surface. What's that? Oh. Giving you a surface. I'm going to ask you to set up the double integral. That finds the volume. Okay. underneath the surface over some region. In the XY plane. So there's 5 of these problems where you have to, I'm going to give you a surface, and I'll give you a square region, say. Okay? And you want to set up the double integral that finds the volume underneath that surface over the square region. Well, that's pretty simple because the limits of integration for x and y will be constants, whatever the square is, 0 to 4, 0 to 4, say, where you're integrating that. You don't have to do the integral, just set up the double integral. Then I may give you a triangular region where you have to find the equation of that line, that's the hypotenuse, so that will serve as one of the limits of integration, say, of the y's, or whatever it happens to be. And there's one of them where I'm going to ask you to do it in polar coordinates, okay? It'll be a circular region and set it up in polar coordinates, okay? Okay, that's 1 through 5. So all you got to do is set up. Then, 6 through 10, I'm going to, and you got to do this one out. Oh, no. Given the lamina. Oh, man. Wait, we did them yesterday, right?
Yeah.
Forget it. I can make this. Whoa, I'm gonna change. No. Given a lamina with a certain density function, I'm going to ask you to find things like mass, moment about the y-axis, moment about the x-axis.
That's a row, right?
What's that?
That's a row. Row x1.
Yes, that's a density function. And then I'm going to ask for x bar and y bar. Now, this is going to be very similar to the one we did. We did a right triangle one. It's going to be very similar to that. Okay? Very similar. It won't be bad. It'll be very similar. 11 to 15. So check out the one I did in class with the right triangle, and you will be okay. What? What? Holy mackerel. All right, this is 11 through 15. You're going to be given Z is a surface in 3 space. And I'm going to give you a density function. This is like the one where we did with the 2 paraboloids, but it's a little bit easier than that. Okay? But I'm going to ask just for the triple integral. You don't have to evaluate these. Find the triple integral that gives you volume.
Gee,
Okay.
R.Burns, you getting like calc 3.5 here.
Well, I know. I think I'm out of control here with this one. Mass. Set up the triple integral that gives you the mass, the volume, moment from the xy plane.
Oh, so you set it up?
Yeah, set it up. Just set it up. Just set them up. Moment from the yz plane. Moment from the last one, the yz. And the last one is y. Oh, I got xz. All right. Well, anyhow, shoot. Xz. Okay. Okay. The only differences between those 3 are what you multiply the distance. The distance from the xy plane, you're going to multiply by a z. Distance from the yz plane, you're going to multiply by an x. And the distance from the xz plane, you multiply by a y. Okay? And you also have the density function in there. That shouldn't be that bad. And then I ask you how to find x bar or y bar or z bar. In other words, make sure you know the definition how you find these things, okay? X bar, for example, would be the moment from the yz plane divided by the mass. Y bar would equal the moment from the xz plane divided by the mass. Z bar would equal to the moment from the xy plane divided by the mass. I'm going to ask you for the definition, basically. 15 says, and then it says the moment from the xz plane.
So
Oh, that's unreasonable.
Liam, I wish I had a class of you. I mean, a whole big class of you. That'd be the greatest thing to have. Yeah. All right, but anyhow. Because he laughs at all my jokes, and he laughs at it. He's good.
My comic relief today.
Yeah, I know all you guys do. What's that?
My comic relief today.
All right, got it, Dave?
So that's 16, that's in with that?
15 was the moment from the XZ plane, and 16 was one of those definitions.
But this is 11 to 15. So there's a...
Oh, yeah. It says, so 16 would be like a separate thing in general, how to find that. It really wouldn't be part of that. I see. Good point. And then...
Oh, is that not a joke? Sorry.
You guys are all good. You're all good.
Not as better.
17 through 20. Oh, my. Holy moly. All right, well, I'll tell you what. We got a sphere, and you're going to have to do something similar to what we just did with a sphere. So you're given a sphere. And set up the triple integrals. Define them. To find mass, in rectangular, cylindrical, spherical coordinates, so you have triple integral and rectangular, triple integral and spherical, and triple integral and cylindrical. And when I ask for the spherical and the cylindrical, as far as that matter, I'm telling you, in the cylindrical, I tell you to use r, dz, dr, d theta. So I'm telling you what it is. It's an r, dr, d theta, r, dz, dr, d theta. And when I tell you to use spherical coordinates, I put it in rho squared sine phi. In other words, I give you the integrating factor. You don't have to memorize the integrating factor. I give that to you. Okay?
Giveaway.
Well, the weird thing is, though, I put it in the spherical one, it's a d rho, d theta, d phi order. I reversed the order for some reason. I don't know why. But you know what? That's not going to make a whit of difference.
Right?
What's that?
I'm not evaluating it?
No, you're not. Oh, except the very end, yes. The last question. The last question is, find the mass. So what you have to do is evaluate it for one of those, whatever is easiest to do.
Just the math?
Just the mass. That is your test for Thursday. Tomorrow, I will take any questions you have on anything at all. And Thursday, we'll have the test. And wait, tomorrow, I should do the lab. I got to do the lab then tomorrow. Tomorrow I'll do the lab. Because we got yet another lab. Boy, constant lab. Speaking of lab, Dan, how you doing?
He heard laugh.
He heard me say it and he came in.
If you do the lab tomorrow, could you have it do a bit later? Because it's supposed to be like...
Yeah, we can make the lab later on, a week from Friday. Yeah, we can do that. That's
Want to
fine.
go over Friday?
What's that?
Should we go over Friday?
Yeah, we could, sure.
Unless we don't have any questions tomorrow.
Yeah, we'll see. I'll have it ready for tomorrow. We'll see what happens.
I'm gonna bring this to last questions.
What was what?
This is last quadrant.
Last chapter is on work done in a variable force field or vector field. In math, we call it a vector field, and in physics, it's a force field. So what happens is we're moving a particle in a force field. The force is constantly changing. And what we have to do that is a line integral. So we're doing line integrals, which is maybe something you did in physics 2 already. Or physics 1.
Yeah.
What's that?
Yeah, what we're gonna do in the next chapter.
Oh, you told me. There you go. Any questions?
Can I get the notes from yesterday?
Notes from yesterday. Yes, I believe they're on my desk. Either that or Nick had them. I think they're on my desk.
And then beef.
All right. See you guys tomorrow. I'll take any questions you have. Notes from yesterday. Let's take a look. Teddy, let's go find them.
You